This is the lecture of the week 2, Relative Entropy and Mutual Information. I'm Hikmet Kamberay, a professor at the Faculty of Engineering, International Balkan University. An outline of the talk is as the following: relative entropy, mutual information, relationship entropy and mutual information, chain rules, and Jansen's inequality. First, I'll talk about the relative entropy. By definition, the relative entropy, or Kullback-Leibler distance between two probability mass functions, p of x and q of x, is defined as d of p from q equal to sum of all x's from the alphabet set chi p of x times log with base 2 of p of x over q of x. It can be seen that from equation 1 we can write d of p from q, it is equal to expected value with probability distribution p of x of this function log with base 2 of the ratio p of x over q of x. In using equation 1 and 2, we have to note that we use 0 log with base 2 of 0 over 0 as 0, 0 times log with base 2 of 0 over q of x as 0, and p of x times log with base 2 of p of x over 0 as infinite. Therefore, exists a x from the alphabet set chi that if p of x is greater than 0 and q of x it is equal to 0, implies that d of p from q it is equal to 0. As a remark, the relative entropy is a measure of the distance between two distributions. From statistics viewpoint, it is the expected value of the logarithm of the likelihood ratio. From the information theory viewpoint, it is a measure of the inefficiency of assuming that the distribution of a discrete random variable x is q of x, when the true distribution is p of x. That is, to describe the discrete random variable x, we could use a code of length h of p if we have to use p of x as property mass function for x. However, if we assume q of x as a property mass function of x, the code length would be larger, h of p plus d of p from q. So it is larger by the amount of relative entropy, d of p from q. If q of x it is equal to p of x, then relative entropy it is equal to 0. Now we are going to give a definition of the independent discrete random variables from the probability and statistics viewpoint. If x and y are two discrete random variables with joint property mass function p of x and y from the alphabets chi and epsilon respectively, marginal property mass functions p of x and p of y, by definition, x and y are independent random variables if and only if p of x and y it is written as a product p of x times p of y. As a consequence, if the joint property mass function is different from the product of marginals, p of x and y different from p of x times p of y, then x and y are dependent random variables. To quantify the amount of the dependence between the random variables x and y, the Kullback-Leibler distance d of p from q can be used, with p taken as p of x and y and q taken as product of marginals p of x times p of y. The relative entropy, or Kullback-Leibler distance between the joint property mass function and the product of marginals p of x times p of y is called mutual information, and this is given on the next slide. So on the next slide I'm going to introduce the mutual information definition. Consider x and y are two discrete random variables with joint property mass function p of x and y from the alphabets chi and epsilon respectively, with marginal property mass function p of x and p of y. The mutual information I of x and y is the relative entropy between the joint property mass function p of x and y and the product of marginal property mass functions p of x times p of y, and it is given as the following: I between x and y equals the relative entropy between p of x and y and the product p of x times p of y, and it is equal to double sum of x over the alphabet set chi and y over the alphabet set epsilon, p of x and y times the log with base 2 of the ratio p of x and y over the product p of x times p of y. It can be seen that the mutual information between x and y, which by definition equal the double sum of x over chi and y over epsilon, p of x and y times log with base 2 of the ratio p of x and y over p of x, p of y equals the expected value with probability distribution joint probability mass function p of x and y of this quantity little I between x and y. Here, the E of p of x and y denotes the expected value with probability p of x and y, and small letter I of x and y, which is given as log with base 2 of the ratio p of x and y over the product p of x times p of y, denotes an instant of the mutual information measured for a pair x and y, called here the local mutual information. That indicates that small letter I, x and y is a random variable, and it is a measure of an instant of the mutual information between the random variables x and y. On the other hand, the big I, x and y is a measure of the expected value of little I, x and y, with property mass function p of x and y, and hence the mutual information between x and y can be seen as the average common information between x and y. A Venn diagram representation of the mutual information is shown on this graph. On blue, I've shown the Shannon entropy h of x, and in red, Shannon entropy of the random variable y. Then the joint entropy between x and y, it is the union of the h of x and h of y, and the mutual information represent the intersection between the two circles, one that represent the h of x and the other one that represent h of y. Based on this one, we can say that the mutual information, it is the average common information between x and y random variables. We are going to illustrate all this with an example. Consider a discrete random variable x, taking the values from the alphabet chi with elements 0 and 1. Let p of x and q of x be two property mass functions on x, on chi set. P of x, it is equal to 1 minus r for x equal to 0, and r for x equal to 1. Q of x, it is equal to 1 minus s for x equal to 0, and s for x equal to 1. I have to calculate the relative entropy between P and Q and P. Using the definition of the relative entropy as d of p from q, it is equal to sum of all x's from chi set p of x log with base 2 of p of x over q of x. Since there are two elements on the alphabet set, then we write the sum as p of 0 log with base 2 of p of 0 over q of 0 plus p of 1 log with base 2 of p of 1 over q of 1, which is equal to 1 minus r log with base 2 of 1 minus r over 1 minus s plus r log with base 2 of r over s. Next, we calculate d of q from p. Now, again, from the definition, we can write the d of q from p as sum of all x's from chi, q of x now, log with base 2 of q of x over p of x. Then again, chi as the element 0 and 1, so we can arrive to the second line, q of 0 log with base 2 of q of 0 over p of 0 plus q of 1 log with base 2 of q of 1 over p of 1. Replace q of 0, p of 0, q of 1, p of 1, and we get 1 minus s log with base 2 of 1 minus s over 1 minus r plus s times log with base 2 of s over r. Now, we can notice that if r it is equal to s, then p of x it is equal to q of x, and the relative entropy of p from q and q from p are both equal to 0. On the other hand, for r equal to 1 over 2 and s equal to 1 over 4, we get d of p from q as 1 over 2 log with base 2 of 1 over 2 over 3 over 4 plus 1 over 2 log with base 2 of 1 over 2 over 1 over 4. Then we get the second line, 1 over 2 log with base 2 of 2 over 3 plus 1 over 2 log with base 2 of 2. Log with base 2 of 2 it is equal to 1. Then we finally can arrive to the final term that it is equal to 1 minus 1 over 2 log with base 2 of 3. Moreover, this is equal to 0.2075 bits or 0.2075 bits. I want to also mention, then arriving on the third line, we have also used the property of the logarithm on the second line, where it says that log with base 2 of 2 over 3 it is equal to log with base 2 of 2 minus log with base 2 of 3. Now the same thing for the r equal to 1 over 2 and s equal to 1 over 4 we get for the relative entropy between q and p. This one, 3 over 4 log with base 2 of 3 over 4 over 1 over 2 plus 1 over 4 log with base 2 of 1 over 4 over 1 over 2. Again, if we simplify, then we get 3 over 4 log with base 2 of 3 over 2 plus 1 over 4 log with base 2 of 1 over 2. Again, we use the properties of the logarithm. Log with base 2 of 3 over 2, it is equal to log with base 2 of 3 minus log with base 2 of 2. And log with base 2 of 1 over 2, it is minus log with base 2 of 2. And moreover, log with base 2 of 2, it is equal to 1. Then we arrive that it is all equal to 3 over 4 log with base 2 of 3 minus 1, which is equal to 0.1887 bits. Now we can notice that the relative entropy of P from Q and D of Q from P are different. Next, we discuss the relationship between the entropy and the mutual information. Starting with the definition of the mutual information. So the mutual information between x and y, it is equal to the double sum of x over the alphabet set chi and y over alphabet set epsilon. P of x and y log with base 2 of p of x and y over p of x times p of y. What we do now, to arrive on the second line, we group together p of x and y over p of y and y. Now this one is going to give me, based on the property in statistic and the definition of the conditional probability, this will give me the probability of x conditioned on y. Then I arrive on the second line. Now on the second line, I group together log with base 2 of this ratio p of x over x given y over p of x. Now this one I use the property of logarithm, and this is the difference of the two logarithms. Log with base 2 of p of x conditioned on y minus log with base 2 of p of x. Now I write this, the third line, as two sums. The first is a double sum of x over x, chi, and y over epsilon. P of x and y, log with base 2 of p of x given y. And minus double sum p of x in chi and p of y in epsilon. P of x and y, log with base 2 of p of x. Now, from this line, if you see the term in green, sum of all y's of the joint property mass function p of x and y. Based on the last week lecture, this will give me the marginal property mass function with respect to x. Then I am on this line now, next line. The first sum, double sum, gives me minus the conditional entropy of x given y, and the next sum gives me minus. I'm remaining just with the sum of x over chi set, p of x, log with base 2 of p of x. Now the second term gives me the entropy with respect to the x random variable. Then I rearrange it and write it h of x minus h of x given y. Similarly, starting with the definition again of the mutual information, I between x and y, double sum of x over chi set and y over epsilon, p of x and y, log with base 2 of p of x and y over p of x times p of y. Now I group on the first line p of x and y over p of x and x, and this will give me the conditional probability of y given x. Then I'll have double sum again, p of x and y, log with base 2 of p of y conditional on x over p of y. Now I use the property of logarithm again, log with base 2 of the ratio of p of y given x over p of y can be written as a difference of the two logarithms. Logarithm with base 2 of p of y given x and minus logarithm with base 2 of p of y. Now I write this one as two terms. The first is a double sum of x over chi set and epsilon over epsilon of p of x and y log with base 2 of p of y given x minus sum of all x's from chi set, sum of all y's from epsilon, p of x and y log with base 2 of p of y. Now I see this on the second term, I see the sum of x from chi set and p of x and y. So terms that are highlighted, indicated in green. Then this will give me the marginal of property mass function with respect to y. And the first term will give me, with minus in front, the conditional entropy of y given x. Then I'll have minus h of y given x minus sum of all y's from epsilon, p of y of y log with base 2 of p of y. Now this second term gives me the entropy of y random variable. Then I rearrange it as h of y minus h of y given x. So I can summarize what just said, that the information, mutual information between x and y, it is either equal to h of x minus h of x given y, or h of y minus h of y given x. I could demonstrate this one as a Venn diagram. So on this Venn diagram I have shown in blue, circled in blue, the h of x, and what is circled in red, it is h of y. Now what is shown here as a shadow area in gray, this gives me h of x given y, and what is shaded in yellow gives me h of y given x. Then what is shaded in brown here gives me the mutual information between x and y. As a remark, I could say that the mutual information I between x and y is the reduction in the uncertainty of one of the random variables because of the knowledge of the other random variable. From the week 1 lecture, we have that the joint entropy of x and y, it is either equal to h of x plus h of y given x, or h of y plus h of x given y. Therefore, I could write the mutual information between x and y as, we just derived, h of x minus h of x given y equal to h of x minus h of x given y can be written as h of x and y minus h of y. Then if I open the brackets and rearrange it, then you get equal to h of x plus h of y minus h of x and y. Right? And this makes sense, right? Because h of x plus h of y is going to give me the union of h of x and h of y plus the mutual information between x and y. So to extract the mutual information between x and y, you have to get h of x plus h of y and subtract the union, right, of between x and y, of the entropy between x and y. Now, we can give the concept of the self-information. We can start with the formula of the mutual information between x and y as h of x plus h of y minus h of x and y. Now, if we assume that y is equal to x, then we get I, or mutual information between x and x. And this is equal to h of x plus h of x minus h of x and x. Now the joint entropy between x and x, it is the h of x itself, and I get h of x plus h of x minus h of x. One h of x cancels out, then I am left with h of x. Then I could see that the mutual information between x and x, it is simply the entropy of x. So that indicates that the mutual information of a random variable with itself equals the entropy of that random variable. Therefore, the entropy can also be called self-information. Or, as a remark, the entropy h of x of a discrete random variable x is interpreted as the information we would gain if the random variable x is completely described, but it is still missing, all right, information, because it is a discrete random variable not completely described. All right, so this is something that we also mentioned last week. Now we consider an example. Suppose the joint property mass function p of x and y of the discrete random variable x and y, which is given as. This is an example that we also considered similar example last week. Right. So I can explain a little here. So x takes the value 1, 2, 3, and 4, and y takes also the value 1, 2, 3, and 4. What you see on here on this matrix, this gives me the joint property mass function. So that means 1 over 8, it is the p of 1 and 1. And p of 2 and 1, it is 1 over 16. And p of 3 and 1, it is 1 over 32. And p of 4 and 1, it is 1 over 32. Now if you go on the second row, this will give me p of 1 and 2, 1 over 16. This will give me p of 2 and 2, 1 over 8. And this will give me p of 3 and 2, 1 over 32. And this will give me p of 4 and 2. And if I go on the third line, y is equal to 3, and x moves 1, 2, 3, and 4. And to read the joint property mass function as 1 over 16, 1 over 16, 1 over 16, 1 over 16. On the last row, y is equal to 4, and x moves 1, 2, 3, and 4. So I have p of 1 and 4, 1 over 4, then p of 2, 4, 3, 4, and 4, 4 are all equal to 0. Now to calculate the marginal with respect to y random variable, then we can sum along the row. So if I sum along the first row, then I take p of y of 1, and it is 1 over 4. If I sum along the second row, then this will give me p of y of 2, which is equal to 1 over 4, and so on. If we sum along the third row, you get p of y of 3, 1 over 4, and along the fourth row, you get p of y of 4, which is 1 over 4. Similarly, if I sum along the columns, for example, along the column with x equal to 1, then I get p of x of 1, which is 1 over 2. Along the column with x equal to 2, then I get p of x of 2, which is 1 over 4. And if I sum up along the column with x equal to 3, then I get p of x of 3, which is 1 over 8. And if I sum along this column here with x equal to 4, then I get p of x of 4, which is 1 over 8. So this is something that we could have also explained on the last exercise on the week number 1. We just did it. All right. Now the purpose on this exercise is to calculate the mutual information between x and y. Now, from the week number 1, we calculated that h of x it was equal to 7 over 4 bits, h of y it was 2 bits, and h of x and y was 27 over 8 bits. Therefore, the mutual information between x and y it is equal to h of x plus h of y minus h of x and y, which is equal to 7 over 4 plus 2 minus 27 over 8. And this is equal to 14 plus 16 minus 27 over 8. And this is equal to 3 over 8, or 0.375 bits. Next, we are going to learn about the so-called chain rules. Now first, we are introducing a theorem about the chain rule of the entropy. Consider n discrete random variables, let's say x1, x2, xn, with joint probability mass function p of x1, x2, xn. The joint entropy can be expressed as the following: h of x1, x2 up to xn, it is equal to the sum of I from 1 to n of the conditional entropies h of xi given xi minus 1, xi minus 2, and so on x1. This is known as the chain rule for entropy. Now, since this is a theorem, we can prove this one. Now, for this one, we use a formula which is known from the property and statistics, which says that the joint property mass function of x1, x2, xn, which are all discrete random variables, it is equal to product of I from 1 to n of conditional probabilities p of xi conditioned on xi minus 1, xi minus 2, and so on x1. Now we can use this one to calculate the joint entropy, which can be written as the following: the joint entropy h of x1, x2, and xn, it is equal to minus sum of all x1, x2, xn, p of x1, x2, xn, log with base 2 of p of x1, x2, xn. Now I can replace the joint probability mass function within the log with base 2 function. Then I have minus the first sum remains as it is, sum of x1 up to xn, p of x1, x2, xn. Then log with base 2 is written as product of I from 1 to n, p of xi conditioned on xi minus 1, xi minus 2, x1. Moreover, I use the property of the logarithm. Logarithm of any base, in that case of base 2, of the product equals to the sum of the logarithms of each term of the product. So I arrive on the third line, equal to minus sum of x1, x2, xn, p of x1, x2, xn, sum of I from 1 to n, log with base 2 of conditional probability, p of xi conditioned on xi minus 1, xi minus 2, x1. Next, I switch the position of the sums. So I write first the sum of I from 1 to n, and second the sum of x1, x2, xn. Then I leave the other terms as they are, minus in front, p of x1, x2, xn, log with base 2 of p of xi conditioned on xi minus 1, xi minus 2, x1. Then it continues. What I do, the second sum I split in two sums, for the reason that I'm going to explain in a moment. So I have the first sum as it is, minus sum of I from 1 to n. Then the second sum is split on two sums. First the sum of x1, x2 up to xi, and the second sum xi plus 1 up to xn. Then I have as it is p of x1, x2, xn. Then log with base 2 of conditional probability, p of xi conditional on xi minus 1, xi minus 2, x1. Now the reason that I express the second sum as two sums is the following. Because if I see inside the log with base 2, the condition probability depend on xi, xi minus 1, xi minus 2, and so on, x1, but does not depend on xi plus 1, and so on, up to xn. However, the p of joint property mass function, p of x1, x2, xn, depends on all terms. However, if you sum the joint property mass function for xi plus 1, xi plus 2 up to xn, I obtain the so-called marginal property mass function with respect to x1, x2, xi, and this is what I did. So if I arrive on the third line, this is a double sum minus a sum of I from 1 to n, and the second sum now it is x1, x2, xi of the marginal p of x1, x2, xi. Then I have log with base 2 of the condition probability, p of xi conditioned on xi minus 1, xi minus 2, x1. Now if I see this one, the second sum with a minus in front gives me the so-called conditional entropy of h of xi conditional on xi minus 1, xi minus 2, x1. Then I obtain the last line, sum of I from 1 to n, conditional entropy h of x1 conditional on xi minus 1, xi minus 2, x1. And this is what we wanted to prove. Now another definition is the conditional mutual information. Now by definition, let x, y, and z be three discrete random variables with joint property mass function p of x, y, and z. Then the conditional mutual information of the random variables x and y given z, it is defined by I between x and y given z, it is equal to h of x conditional on z minus h of x conditional on y and z, which is equal to the triple sum over x, y, and z, p of x and y and z, log with base 2 of this ratio, p of x and y conditional on z over p of x conditional z and p of y conditional z. As a remark 1, the mutual information between x and y given z represents the reduction in the uncertainty of x due to the knowledge of y when z is given. It can be found that the mutual information between x and y given z, it is also equal to the triple sum over x, y, and z of this product of the joint property mass function of x, y, and z times the little I between x and y given z, which it is furthermore equal to the expected value with probability distribution, the joint property mass function p of x and y and z of little I between x and y given z, where the little I between x and y given z equals to the log with base 2 of this ratio, of the ratio of the p of x and y given z over p of x given z times p of y given z. Here, the little I between x and y given z represents an instance of the conditional mutual information, called here the local conditional mutual information. And it is called conditional mutual information because it calculates an instant of the mutual information between x and y given z. Therefore, that indicates that I between x and y given z is a random variable. And moreover, we arrive to the remark number 2, that the big I, which is the mutual information between x and y given z, can be interpreted as the average amount of information contained in y about x that is not contained in z. Therefore, it is an information flow measure from y to x. This is a very important quantity of the measure of the information flow, not just about the discrete random variables, but also about the random process. And a few lectures later, we'll describe a measure of the information flow, which is called transfer entropy between processes which describe discrete random processes. For example, time series, and this has the applications on the physics. If you want to determine the information flow between the dynamical systems, it can be used on the finance. If you want to describe the information flow between the time series, it can be used also in biology and perhaps in other fields as well. As a Venn diagram of the conditional mutual information can be used the following. In this Venn diagram, I have shown 3 circles. In blue, I have shown the circle that represent the h of x, so the entropy of x random variable. In red, I have shown the entropy of the y random variable. Then in green, I have shown the entropy of the z random variable. Moreover, I have indicated here these quantities. The entropy of x given z here, which is represented by this. So if you follow my cursor, then you'll find out that it is all this one. Up to here. This is the entropy of x conditional z. Then I have the next one. I'm going to represent the entropy of x conditional on y and z. Then this one, it is indicated as it's shown on here. So it is this part on here. So if you start from here, so be this one. So what is on blue up to here, right? Then follows the red part up to here, then the green part up to here. This, it is the entropy of x conditioned on y and z. Now, the difference between these two, all right, then this is going to give me the so-called the mutual information between x and y given z, which is this part that I'm going to follow with my cursor, this one, only this part. Clear? And it makes sense that this is the difference between the h x given z minus h of x given y and z. All right? So this is something that we showed before. To note on this, it can be seen that if x and y are independent given z, that is no information flow, then the mutual information, condition mutual information between x and y given z, it is equal to 0. Now, with this definition of the conditional mutual information, we can arrive to another theorem, which is chain rule of information. Now, let x1, x2, xn, and y be discrete random variables. Then the mutual information between x1, x2, and xn and y is defined as I between x1, x2, xn, and y, and it is equal to sum of I from 1 to n of the conditional mutual information I between xi and y given xi minus 1, xi minus 2, and x1. Now this is a theorem. We have to prove this one. To prove this one, we use the so-called chain rule of the joint entropy and definition of conditional mutual information. So first we start with the formula of the relation of the mutual information with entropies in the general case. So we have the mutual information between x1, x2, and xn and y, which is equal to the difference between the joint entropy of x1, x2, xn minus conditional entropy of x1, x2, xn on y. Then this is the using the relation of the mutual information with entropies. Then next we use on each term on the right hand side of the first equation the chain rule of entropies. For the first term of the joint entropy between x1 and xn random variable, then we can write it as a sum of I from 1 to n of conditional entropies of h of xi on xi minus 1, xi minus 2, x1 minus on the second term, then we write sum of I from 1 to n conditional entropy of xi on xi minus 1, xi minus 2, x1, and y. Right? Then we write each term within the sum as one sum, the sum of I from 1 to n. Then on the parenthesis I have the difference between the two conditional entropies, h of xi given xi minus 1, xi minus 2, x1 minus h of xi conditional on xi minus 1, xi minus 2, x1, y. Then I use the formula of the conditional mutual information to arrive to the last line. So if you see on the inside the sum on the parenthesis, this gives me the conditional mutual information between xi and y given xi minus 1, xi minus 2, x1. And this is proof of what we wanted. Now we can demonstrate this one using the Venn diagram. However, the example is simple for n equal to 2. So this means that I have x1, x2, and the y in the variable. Then the theorem that we just proved can be written on this form. The mutual information of x1, x2 between x1 and x2 and y, it is equal to the mutual information between x1 and y plus the conditional mutual information between x2 and y given x1. Now let's see what are all these terms. Now if I want the first term on the right hand side, which is the mutual information between x1 and y. So the blue circle gives me the entropy of x1. The red circle gives me the entropy of y. And the green circle gives me the entropy of x2. Now the mutual information between x1 and y here, it is, I'm just following my cursor. It is all this area which is on here, or can be seen as a sum of two terms, of this term on here and this term on here. Then I am representing the second term on the right hand side, the mutual information between x2 and y given x1. Then what is this term? This will be the mutual information between x2 and y given x1. So you first find the mutual information between x2 and y and subtract the x1 part. So we start the mutual information between x2 and y. All right? Between x2 and y, it is all this part. All right, all this part. Now if I subtract, because x1 it is given, I subtract this part on here, then you are left at the mutual information between x2 and y given x1, it is all this part here. Right? Now if I sum up the mutual information between x1 and y, which is all this part, and this part on here, then you get all this part on here, which is equal to the mutual information of x1, x2, and y. All right, so this is a simple proof of what we wanted to show, but for the simple case of inequality 2. Next definition is the so-called conditional relative entropy. Now let x and y be two discrete random variables, and p of x and y and q of x and y two joint probability mass functions. The conditional relative entropy, which is the distance between two condition probabilities, p of y given x from q of y given x, is the average of relative entropies between the conditional probability mass functions p of y given x and q of y given x averaged over the probability mass function p of x, which is given by this formula. Sum of all x's from alphabet set chi p of x, sum of all y's from the epsilon, p of y given x log with base 2 of p of y given x over q of y given x. Now if you notice, the formula, it is highlighted in two colors, in blue and in red. This is in order to explain the equation 16. So the equation 16 can be seen or as this sentence: the average, which is over the property mass function p of x, of some function, which I'm going to say in a moment. Now this first sentence, the average over the property mass function p of x, which is on the sentence, it is highlighted in blue. On the formula, it gives me the first part of the formula, first sum of all x's from chi alphabet set p of x. Then I continue reading the sentence of relative entropies between the conditional probability mass functions p of y given x and q of y given x. Then I write down the relative entropy, one of these, between the conditional probability mass functions p of y given x and q of y given x. Then based on the definition that we gave it before, this is the sum over all y's from the epsilon, p of y given x log with base 2 of p of y given x over q of y given x. Then all this sentence, the blue plus red, will give you the old formula 16. Now this is a way how you could understand the wording of this definition. Now it can be seen from the equation 16 that the condition relative entropy, which is on the first line of equation 17, it is written based on the definition. So I'm reading again: sum of all x's from the alphabet set chi, p of x, sum of all y's from the alphabet set epsilon, p of y given x, log with base 2 of p of y given x over q of y given x. Now, on the second line, what I have done, since the second sum does not depend on x, right, because it's a sum over y's, then p of x can be put inside the second sum. Then I am writing sum of all x's from chi, sum of all y's from epsilon. Then I have p of x times p of y given x. Then log with base 2 of the ratio as it is on the first line. Now, the one that shows on the red on the second line can be grouped together. P of x times p of y given x. Then this gives me the joint property mass function between x and y. Then I go on the third line and write double sum over x and over y. Then I have p of x and y, log with base 2 of the same ratio p of y given x over q of y given x. Now this last line gives me the expected value with probability distribution, the property mass function p of x and y of this function, log with base 2 of this ratio p of y given x over q of y given x. Now we can arrive to the so-called chain rule of relative entropy. Now the theorem says like this: the chain rule for relative entropy is given as relative entropy between joint probability mass function p and q. It is equal to the relative entropy between the marginal probability mass function p of x, q of x, plus the relative entropy between the conditional probabilities p of y given x from q of y given x. Now, as a proof of this one, to prove this theorem, we continue d of p of x and y from q of x and y, it is equal to sum of all x's from x, sum of all y's from y, p of x and y, log with base 2 of p of x and y over q of x and y. Now, we can express p of x and y as p of x times p of y conditional on x. Then the joint property mass function q of x and y can be written q of x times q of y conditional on x. Then we arrive on the second line: double sum over x and y, p of x and y log with base 2 of p of x times p of y given x over q of x times q of y given x. Then on the third line, we split the log on the second line with base 2 of this ratio of products into two terms. One, it is the p of x over q of x times p of y given x over q of y given x. Then we can write this one as a sum of two terms. First term is a double sum over x and y of p of x and y log with base 2 of p of x over q of x. And the second term, it is the double sum over x and y of p of x and y log with base 2 of p of y given x over q of y given x. However, the first term gives me the relative entropy between the marginals p of x from q of x plus the second term gives me the conditional relative entropy p of y given x from q of y given x. And this proves what we wanted to show. Next, I'm going to talk about the Jansen's inequality. Before I start with this one, first I'm going to give some definition from the mathematics or convex function. By definition, a function f of x is convex over interval ab if for every x1, x2 in the interval ab and a lambda which is between 0 and 1, including 0 and 1, we have that f of lambda x1 plus 1 minus lambda x2, it is less equal to lambda f of x1 plus 1 minus lambda f of x2. Now this is a definition. Moreover, the equality on the equation 19, right, holds if a function f of x is strictly convex and if the equation 19 holds for lambda equal to 0 and lambda equal to 1. Now to illustrate graphically the convex function, consider the following graph. Consider a x and y graph. In black it is shown the f of x function. Right? Then we take 2 points, x1 and x2, which are on the interval between a and b. Then we draw a straight line between these 2 points, x1 and x2, which is the red line that is shown on here. Then we pick up along the x-axis a point x, which is equal to lambda x1 plus 1 minus lambda x2. Then we map this point along the y-axis once according to the f of x function, the black line, and the other time according to the red curve. Right? Now if I map it according to the f of x function, then you will get f of x, and this is the point of the intersection. Then if you map it along the red line, and this is the point of intersection, then we map it on lambda f of x1 plus 1 minus lambda f of x2. Now we can notice then the red dot here, bullet, it is always above the blue bullet, and this holds for every point on the red curve. So we can say now that if the points of the red curve are above the points of the function f of x, then by definition f of x graphically is a convex function. So this is the way how we can judge it. Now we can give also the definition of concave function. A function f of x is concave over a certain interval ab if the function minus f of x is convex. Similarly, graphically we can interpret it in this way. So I have a xy axis, then again the black curve gives me the f of x function. Then we pick up 2 points along the x-axis, x1 and x2. Then we draw a straight line between these 2 points on the f of x function. Then we pick up a x along the x-axis, which is lambda x1 plus 1 minus lambda x2. Then we map this one along the y-axis, once along the red curve and once along the f of x function. Along the f of x function, it is as transforming the blue point into the y-axis, which is f of lambda x1 plus 1 minus lambda times x2. And along the according to the red curve, then this is transformed as lambda times f of x1 plus 1 minus lambda f of x2. Now we can notice that the red dot here point, it is always below the f of x. And this is for every point between x1 and x2 on the red curve. All these points are below the f of x function. If this is the case, then f of x, it is a concave function. So this is kind of illustration. Now we can go to a theorem now, which is kind of mathematical theorem to find the minimum or maximum of function, but we are going to reformulate slightly differently. If the function f of x has a second derivative that is non-negative, this means that the second derivative of x, it is greater or equal to 0, over interval a, b, the function is convex over that interval. If the second derivative function is positive, this means that the second derivative of x, it is rigorously greater than 0, then the function is strictly convex. Now we can prove this theorem. All right? First, we can start writing the Taylor expansion of f of x around some point x0 in the interval ab. Then we can write f of x equal to f of x0 plus the first derivative of f with respect to x evaluated at x0 times x minus x0 plus the second derivative divided by 2 evaluated at some point x star x minus x0 all square. X star, it is a point between x0 and x, including x0 and x. Now, using the hypothesis of the theorem, which says that the second derivative evaluated as at x star, it is non-negative, so it is greater or equal to 0. Therefore, since f second derivative at x0, it is greater than 0, so does also x minus x0 square. If you divide by 2 a positive number, then we obtain a non-negative number for every x. Right? Now, if we continue now on the next slide, we take first x0 as lambda x1 plus 1 minus lambda x2. And for x equal to x0, x1, we have f of x1 greater or equal to f of x0 plus f prime, which is the first derivative at x0, times 1 minus lambda times x1 minus x2. Now for the same x0, but for x equal to x2, we get f of x2 greater or equal to f of x0 plus f prime, first derivative, at x0 times lambda times x minus x1. Now, if you multiply equation 20 and 21 by 1 minus lambda equation 20 by 21 and by lambda equation 20 and adding side by side, then we get the following: lambda times f of x1 plus 1 minus lambda f of x2, and all this one, it is greater or equal to f of x0. Now, which proves, based on the definition, that f of x is a convex function. Now, about the proving the second part of the theorem, if the second derivative function is positive, so this means that second derivative at x, it is strictly greater than 0, then following the same proof, right, same lines, it can be shown that the function is strictly convex. So this means that lambda f of x1 plus 1 minus lambda f of x2, it is greater rigorously than f of x0 for lambda different from 0 and lambda different from 1. Okay? If lambda it is equal to 0 or lambda it is equal to 1, then you get for lambda equal to 0, you get f of x2 equal to f of x1, x2 f of x0, and if lambda equal to 1, you get f of x1 equal to f of x0, which is based on the definition of the convex function. Now, we introduce the so-called Jansen's inequality. The theorem says like this: if f is a convex function and x is a random variable, then the expected value of the f of x, it is greater or equal to the value of the function at the expected value of x. If f is a strictly convex function, equality in equation 22 implies that x, it is equal to simply expected value of x with probability 1. That is, x is a constant. Now, how we can prove this? We assume that x is a discrete random variable, and we use the mathematical induction to prove the theorem. First, we start with a 2 mass point distribution. This means that I have a probability distribution function evaluated at x1 and x2, 2 points. Now, in that case, the expected value of the f of x, it is equal to f of x1 plus p of x1 plus f of x2 p of x2. And I want to show that this is greater or equal to f of the expected value of x, which is equal to x1 times p of x1 plus x2 p of x2. If we denote p of x1 by lambda, and I have the right to do this one because lambda has to be a number between 0 and 1. Indeed, p of x, which is a property mass function value, it is a number between 0 and 1 by definition of the property mass function. Moreover, p of x2 is going to be 1 minus lambda. Why? Because p of x1 plus p of x2, it is equal to 1. And then we get that f of x1 times lambda plus f of x2 times 1 minus lambda, it is greater or equal to f of x1 lambda plus x2 1 minus lambda. Now this proves that f of x is a convex function based on the definition of the convex function. Now we assume that this is true also for a k minus 1 mass point distribution. That is, sum of I from 1 to k minus 1, f of xi times p of xi, which will give me the expected value of f of x, it is greater or equal to f, the expected value of x, which is sum of I from 1 to k minus 1, xi p of xi. Now this is assumed to be true. Now for the mathematical induction to be shown true, we have to prove that it holds for a k mass point distribution. That is, I have to show that sum of I from 1 to k, f of xi times p of xi, it is greater or equal to f of the sum of I from 1 to k, xi p of xi. Now for that we write this number first, p prime of xi, which is equal to p of xi 1 minus p of xk, for I 1 to k minus 1. It can be shown that pi primes forms a probability distribution. To show this one, first we show that normalization condition is satisfied. So for that, if I take the sum of I from 1 to k minus 1 of p prime xi, which is equal to the sum of I from 1 to k minus 1, p of xi over 1 minus p of xk. And this is equal to 1 over 1 minus p of xk, sum of I from 1 to k minus 1 p of xi. This is because the ratio 1 over 1 minus p of xk does not depend on index I. Then on the next line, the sum of I from 1 to k minus 1 can be written as the sum of I from 1 to k p of xi if I subtract the term that I added, which is for I equal to k, p of xk. Then I get 1 over 1 minus p of xk, sum of I from 1 to k p of xi minus p of xk, and this is equal to, now since p of xi's are a probability mass function, then they are normalized to 1 for a k-point mass function distribution. So this means that sum of I from 1 to k p of xi, it is equal to 1. Then I get 1 over 1 minus p of xk, 1 minus p of xk. Now this 1 minus p of xk cancels out or simplifies, then you get equal to 1, which proves that is normalized. Moreover, based on the formula, one that is given on this slide, you could notice that p prime of xi are numbers between 0 and 1 for every I be 1, 2, and k minus 1. So we can say that p of I forms a probability distribution. Then we prove next thing. So we start with sum of I from 1 to k, p of xi, f of xi. Then I can write this one as p of xk, f of xk, plus sum of I from 1 to k minus 1, p of xi, f of xi. So from the sum on the left-hand side, I have separated the last term for I equal to k, so to say, which gives me the first term on the right-hand side. Then what is left, I from 1 to k minus 1, form the second term of the right-hand side. Now, based on the hypothesis, right, or first we express p of xi from the p prime xi, which obtain the second line. So the first term on the right hand side of the first line remains as it is, p of xk, f of xk, plus then p of xi can be written as p prime xi times 1 minus p of xk. But 1 minus p of xk does not depend on I can bring it outside the sum. Then I'm left with sum of I from 1 to k minus 1, p prime xi, f of xi. Now I can use the so-called hypothesis. So this means the case for a k minus 1 mass point distribution. So this means that if I use this one, what is highlighted in red, the sum becomes greater or equal to f of sum of I from 1 to k minus 1, p prime xi times xi. Then the rest of the terms, which are on black, remains as they are on the second line. Now if I see the third line, then I can apply the basis step. So this means a 2-point mass distribution, where one it is p of xk and the other one it is 1 minus p of xk. Right? Then I have f at xk, then I have f at the sum of I from 1 to k minus 1, p prime xi times xi. Then if I use this one, then this is further greater or equal to f of p of xk times xk plus 1 minus p of xk times sum of I from 1 to k minus 1, p prime xi times xi. Right? Now, moreover, if I write this sum, all right, then this will give me p of xk times xk plus 1 minus p of xk times p prime xi xi gives me p of xi, right? Then group together, write this sum from I to k minus 1 as one sum of I from 1 to k, then I get f of sum of I from 1 to k, p of xi. So this is the proof of what I wanted to show. Now, for the second part of the theorem, if f it is a strictly convex function, in that f of lambda x1 plus 1 minus lambda x2, it is less equal to lambda times f of x1 plus 1 minus lambda f of x2. Equality holds only for lambda equal to 0 or lambda equal to 1. That is, x it is a constant. Then the expected value of f of x, it is equal to f of big X, or it is equal to f of expected value of x. So the x, it is equal to the expected value of x, for x being a constant. So this proves the complete theorem. Now we can use the what we have shown so far to prove some properties of the information. The first one, it is the information inequality. So let x be a discrete random variable, and p of x, q of x, two probability mass functions with x from chi alphabet set. Then the relative entropy between p and q, it is non-negative, so it is greater or equal to 0. Equality holds if and only if p of x, it is equal to q of x for every x from the chi alphabet set. To prove this one, first we start with the second part. If p of x, it is equal to q of x, by definition relative entropy, it is equal to 0 for every x from the chi set. Next, we prove the first part of the theorem. We denote by A the set of all x's such that p of x, it is rigorously greater than 0. And note that the logarithm function is strictly concave. And hence minus log function, it is strictly convex. Then minus d relative entropy of p from q, it is equal to minus sum of all x's from A, p of x log with base 2 of p of x over q of x, which is equal to, can be written as sum of all x's from A, p of x log with base 2 of q of x over p of x. So I put the sum inside the logarithm. Then this is using the Jansen inequality. Then this is less equal to log with base 2 of sum of all x from A, p of x, q of x over p of x. Now if I simplify p of x with p of x, then I get the third line, which is equal to log with base 2 of sum of all x's from A, q of x. Now since A, it is a subset of alphabet set chi, then if I write the sum not just over the A but over all alphabet set chi, then this first sum, it is less equal to log with base 2 of sum of all x from chi q of x. Here I have used also the fact that the logarithm function of any base is a monotonically increasing function. Now q of x is a property mass function, so this means that the sum of all x from chi q of x, it is equal to 1. Then log with base 2 of 1 gives me 0. Then we obtain what we wanted. Alright, because I have minus d of p from q less equal to 0, then if I multiply by minus 1 both sides, then I get d of p from q greater or equal to 0. Now this gives me several other properties. One of these, it is non-negativity of the mutual information. And this is the following corollary. For any two discrete random variables, x and y, the mutual information between x and y, it is non-negative. Equality holds if and only if x and y are independent. Now, this is a simple proof, since the mutual information between x and y, it is equal to the relative entropy between the p of x and y and the product p of x times p of y, using the non-negativity of the relative entropy, then the d of p of x and y from p of x times p of y, it is greater or equal to 0. Then this implies that the mutual information between x and y is greater or equal to 0. Equality holds if and only if p of x and y, it is equal to p of x times p of y. But that is if x and y are independent, which it is the proof of the second part of the theorem. Now, another corollary, it is this one, non-negativity of the conditional relative entropy. Consider any two discrete random variables x and y. Then the relative entropy, conditional relative entropy, p of y given x, from q of y given x, it is non-negative. Equality holds if and only if p of y given x, it is equal to q of y given x. Now again, I use the definition of the conditional relative entropy. D of p of x and y from q of x and y, it is equal to the relative entropy of the marginals plus the conditional relative entropy of the conditional probabilities. Knowing that the d of relative entropy of the joint probability mass function is non-negative, so also relative entropy of the marginal probability mass function is non-negative. So this implies that also the second term on the right hand side, which means the conditional relative entropy, must be non-negative. Now, for proving the second part of the theorem, from the definition of the conditional relative entropy, you could see that the conditional relative entropy, it is equal to 0 if and only if the conditional probabilities are the same, are equal. So this means when p of y given x, it is equal to q of y given x, which is a proof of the second part of the theorem. Now another corollary, it is the so-called non-negativity of the conditional mutual information. For any three discrete random variables, x, y, and z, the mutual information between x and y given z, it is non-negative. Equality holds if and only if x and y are independent given z. Now, from the definition of the conditional mutual information, which is equal to the triple sum over x, y, and z of p of x and y and z times the log with base 2 of this ratio of p of x and y given z over p of x given z times p of y given z. Now this is equal to the p of x and y given z. It is written, as it's shown on red, as a ratio of the joint probability mass function of x, y, and z over p of z. Then we obtain the last expression on the first line. Now you could notice, all right, that the last one, it is the relative entropy between p of x, y, and z, and this product p of z, p of x given z, p of y given z. However, based on the previous theorems, this is non-negative, and this implies that also the conditional mutual information is non-negative. Now we prove the second part of the theorem. If x and y are independent given z, then this means that the joint property mass function x, y, and z can be written as product p of z times p of x given z times p of y given z. But this one indicates that the relative entropy is equal to 0. Or we can say that the condition mutual information as equal to it becomes also equal to 0. And that's the proof of the second part. Now, another theorem is the so-called upper limit of the entropy. Let x be a discrete random variable in the alphabet chi with property mass function p of x. Then, the entropy of x, it is less equal to the log with base 2 of the cardinality of the alphabet set chi. So the cardinality of the alphabet set chi is actually the number of elements in the set chi. And the equality holds if and only if x has a uniform distribution over chi set. Now we denote by u of x 1 over cardinality of chi set. And this is a uniform property mass function over chi set. Then the relative entropy between p and u, it is equal to the, based on the definition, sum of all x's from chi, p of x times log with base 2 of p of x over u of x, equal sum of all x's from chi. Then I express u of x as 1 over cardinality of chi set. Then I obtain log with base 2 p of x times cardinality of chi. Then from this we arrive on the second line. We can write the log with base 2 of p of x times the cardinality of chi as a sum of two logs, log with base 2 of p of x plus log with base 2 of cardinality of chi. Then we have two terms. The first is the sum of over all x's p of x log with base 2 of p of x plus the sum over all x's p of x, and the term log with base 2 of cardinality of chi can be brought outside the sum because does not depend on x. Then the first term gives you, on the second line, gives you the minus entropy of x, and on the second term the sum of all x's p of x gives you 1 as normalization condition. Then we are left with just plus log with base 2 of cardinality of chi. Now using the non-negativity of relative entropy, dp from u it is greater or equal to 0, then we get that entropy of x is less equal to the log with base 2 of cardinality of chi. Now to prove the second part of the theorem of the equality, now if x also has a uniform distribution over chi, this means that p of x it is equal to u of x, then the relative entropy becomes distance between u and u, which is equal to 0 on one hand. Then on the other hand, based on what we showed before, it is minus h of x plus log with base 2 of cardinality of chi. Now from here we get that h of x it is equal to log with base 2 of chi, which is the second part of the theorem. Now important theorem, it is the following. Let x and y be two discrete random variables in the alphabet chi and epsilon respectively, with joint property mass function p of x and y. Then conditional entropy of x on y it is less equal to h of x. Equality holds if and only if x and y are independent. Now to prove this one, we start with the relationship between the entropy and the mutual information formula, which says that the mutual information between x and y it is equal to h of x minus h of x given y. And the non-negativity of the mutual information, which means that mutual information between x and y is non-negative, with equality holds if and only if x and y are independent. Then we arrive that h of x minus h of x given y is non-negative, greater or equal to 0. From here, h of x given y it is less or equal to h of x. Right? And equality holds if and only if x and y are independent, which we just showed on the second paragraph. To note from this one, the theorem that the conditional entropy h of x given y it is less or equal to h of x indicates that knowing another random variable y can only reduce the uncertainty on x. That is also known as information does not hurt. Another note it is from the definition of the conditional entropy, h of x given y, which is equal to the sum of all y's from epsilon, p of y times h of x given y equal to y. Therefore, h of x given y less equal to h of x apply only on average. However, instant values h of x given y equal to y may be greater or less than h of x. And we are going to illustrate this one, right, with some examples. First, in a court of law case, a particular new evidence might increase uncertainty, but on the average, the evidence decreases the uncertainty. Another example, in academic publishing area, a particular new experimental measurement might increase uncertainty if it is in contradiction with previous one, but on the average, the new measurement decreases the uncertainty. So we should never stop reproducing results. Independence bound on entropy. Consider x1, x2, xn being n discrete random variables over the joint property mass function p of x1, x2, xn. Then h of x1, x2, xn, so the joint entropy, is less equal to sum of I from 1 to n h of xi, where the equality holds if and only if xi's are independent. Now we can prove this theorem using the chain rule of entropy. Then the joint entropy of x1, x2, xn random variables, it is equal to the sum of I from 1 to n, the conditional entropy of xi on xi minus 1, xi minus 2, and so on x1. Now using the theorem on the conditional entropy, that is condition entropy of xi on xi minus 1, xi minus 2, x1, it is less equal to the h of xi. Then we get that the joint entropy of x1, x2, xn, it is less equal to sum of I from 1 to n, h of xi's. Now, second part, if x1, x2, xn are independent, then the conditional entropy says that the conditional entropy of xi on x given xi minus 1, xi minus 2, x1, it is equal to h of xi for every I. This proves the second part. Now we consider an example. Suppose the joint property mass function p of x and y of the discrete random variable x and y is given as. So we have x random variable which takes the value 1 and 2, and also y takes the value 1 and 2. Then the joint property mass function is such: p of 1, 1 it is 0, p of 2, 1 it is 3 over 4, p of 1, 2 it is 1 over 8, p of 2, 2 it is 1 over 8. Then the marginal with respect to y, we sum along the row, it is 3 over 4, we sum along the second row, 1 over 8 plus 1 over 8 gives you 1 over 4. Then to calculate the margin with respect to x, we sum along the column, 0 plus 1.8, 1.8. Then to find the marginal p of x at 2, we sum along the second row. 3 over 4 plus 1 over 8 gives you 7 over 8. Now we want to calculate h of x given y equal to 1, h of x y given to 2, then h of x given y. Now for this one, we calculate h of x from the formula minus sum of all x from x, p of x log with base 2 of p of x. And this is equal to minus 1 over 8 log with base 2 of 1 over 8 plus 7 over 8 log with base 2 of 7 over 8. And then you get equal to minus 3 over 8 minus 21 over 8 plus 7 over 8 log with base 2 of 7. And this is equal to 0.544 bits. Then the condition probabilities p of x given y. First we get p of 1 given 1, which is p of 1 and 1 over p of y on 1, which is 0 over 3 over 4, 0. P of 1 given 2, it is p of 1 and 2 over p of 2, 1 over 8 over 1 over 4, 1 over 2. P of 2 given 1, it is p of 2 and 1 over p of y given 1, 3 over 4 over 3 over 4, it is 1. P of 2 given 2, it is p of 2 and 2 over p of y on 2, which is 1 over 8 over 1 over 4, 1 over 2. Then h of x given y equal to 1, it is equal to minus sum of all x's, p of x y given 1 log with base 2 of p of x y given 1, which is equal to minus 0 times log with base 2 of 0 plus 1 log with base 2 of 1, which is 0 bit. And h of x given y equal to 2, it is equal to minus sum of all x's, p of x y equal to 2 log with base 2 p of x y equal to 2. And this is equal to minus 1 over 2 log with base 2 of 1 over 2 plus 1 over 2 log with base 2 of 1 over 2, which is 1 bit. Then h of x given y would be the average value of the two values we calculated, h of x given y equal to 1 and h of x y equal to 2, each with probability 3 over 4 and 1 over 4 respectively. Then you get 0.25 bit. Thus, uncertainty on x is increased if y is equal to 2 and decreased if y is equal to 1, but on average, uncertainty in x decreased if we compare h of x given y with h of x that we found on the first line. So, and in the summary, you should know when two discrete random variables are independent from probability and statistics viewpoint. You should be able to calculate the relative entropy and mutual information. You should understand the properties of the relative entropy and mutual information. You should be able to apply the chain rules. You should be able to apply Jansen's inequality. You should be able to calculate the condition entropy of I between x and y, and two discrete random variables x and y, knowing that they join property mass function. As a reference for you, you could follow my lecture notes book on Introduction to Information Theory, published on Lambert Academic Publishing this academic year, or Elements of Information Theory by Carver and Thomas, published on William Science on 2006. Thank you for your attention. See you next week.